Okay, good morning everybody. Thank you for being here at what I consider to be an extremely early time. Like already I'm struggling to be alive in this moment. So in the next 15 minutes I'll try to rapidly present you one of the latest work that I did in collaboration with Alessandro Laio and Antonietta Mira at CISA, which we titled Clustering by the Local Intrinsic Dimension. So I just give you a brief overview of the topic I'll discuss. I will first tell you what the intrinsic dimension is. Then I will quickly present you an approach to estimate the intrinsic dimension, which is called the 2NN approach. Then I will tell you how we extended the 2NN approach to the case of what I will call a variable intrinsic dimension. And finally, I will show you an application of our new method to a molecular dynamics trajectory. What is the intrinsic dimension? So, as you know, data may be defined in a space with many variables. Let's call it capital D. But in most cases, data actually live on a hypersurface of much lower dimension, which we call intrinsic dimension. So this is why, in many cases of interest, even if the space has, let's say, 1,000 variables, maybe the so-called curse of dimensionality does not really apply, because the data, even if the variables are 1,000, maybe live on a hypersurface of 20 variables. So just to make you an example you might be familiar with, so the state of, say, complex physical systems live in a space with, in principle, lives in a space with many variables. Let's say if you have n atoms or elementary particles, the state in phase space is defined by 6n variables. But due to soft and hard constraints, the system moves only in a few directions in phase space, so that the actual trajectory lives on a hypersurface of dimensionality which is much inferior to 6n. So in the remainder of the talk, by small d, I always indicate the intrinsic dimension of the space. Why is it relevant to compute the intrinsic dimension? There are many problems which require actually to compute it. So first of all, obviously, knowing the right intrinsic dimension is important if you want to find the proper target dimension in a dimensionality reduction scheme. Then there might be also, actually there are other important problems for which you really have to know the proper value of the intrinsic dimension. So the reason why we originally started studying this problem was actually to refine a method for density estimation. I will not tell you about this in detail, but so a simple way to estimate the density of points in the space is a so-called k-nearest neighbor estimator, which just takes considers around each point the sphere containing the first k neighbors and estimates the density as k divided by the volume of the sphere containing the points. The problem is that the volume of the sphere is an angular factor times the radius of the sphere to the power of d, where the proper d is not the extrinsic dimension of the space, so the number of coordinates, but is the intrinsic dimension of the surface. How to estimate the intrinsic dimension? There are 1,000 schemes, but essentially the most schemes assume that the data are samples from a given probability distribution. So in the remainder of the talk, by rho, I always indicate the density distribution of the points. Actually, when the density rho is constant, the distances between points follow some scaling laws that depend on d, which in the end allows you to estimate d. The simplest example, and probably something you might even know, is a so-called correlation dimension, and a concept that has been there for now nearly 40 years. So if you take one point and consider the region around the point, the number of points at a given within a given distance from the point scales as a function of the intrinsic dimension. So in the plot I show, imagine that points are on a one-dimensional manifold, so essentially a curved line. The number of points within an epsilon ball scales linearly with the radius of the ball. If they actually lie on a plane, it scales quadratically, and so on. Actually, if the density of point is constant, we have a this scaling law is perfect, and we have a simple way to estimate the intrinsic dimension, which is just considering the distances of the neighbors from each point, take all the distances, and estimate the intrinsic dimension through a linear fit. The problem is that when the density of points is highly variable, which actually occurs nearly always in real data when considering data spaces of various origin, when the density is highly variable, the scaling does not hold. So the estimation based on this scheme fails dramatically. So in a work published 2 years ago in Scientific Reports, my colleagues developed a scheme to estimate the intrinsic dimension in the case of strongly variable density. The scheme is based on two quite broad assumptions. First assumption is that the points are independent samples from a given density. The second assumption is what I call local uniformity, which means that we assume that the density is constant, but only in a very small region, in a region containing the first two neighbors of each point. So, contrary to other methods that really require the density to be constant in the whole space, we just make a much weaker assumption. We assume that the density is approximately constant in the small region defined by a point and its first two neighbors. Under this assumption, if you consider the distances of the first and second neighbor from each point, you actually can derive that the ratio of these distances, which we call mu, follows a given distribution, which is a Pareto distribution that depends parametrically only on a single parameter, which is the intrinsic dimension of the space. So I repeat it because it's a crucial point. So we consider the distances of the first two neighbors of each point. Under weak assumption, the ratio of these distances, so the ratio of the distance of the second neighbor over the distance of the first neighbor of each point, follows a Pareto distribution that depends only on the intrinsic dimension. Then this immediately allows to estimate the intrinsic dimension d from the collective, from the distribution of these ratios, the mu. So there are several ways of performing the fit, but you can either fit the empirical cumulative distribution of the mu, or by a simple manipulation, you can actually transform it to a linear fit. You just have to take the logarithm of 1 minus the empirical cumulative distribution, and you transform the problem to a linear regression problem. This is a technical detail. In any case, once you derive this expression, this distribution for the mu, it's very simple to perform the fit and estimate the intrinsic dimension. Actually, we realized that in some cases of interest, the intrinsic dimension may not be constant in the whole data space. What do I mean by this? So, for instance, imagine that the data actually lie on several hypersurfaces with different intrinsic dimension. So in the cartoon example I'm showing, I imagine that there are 3 manifolds, 2 of dimension 2 and 1 of dimension 3. So imagine your data are living in such a space. So some data are sampled from a manifold of dimension 3, and some other are sampled from a manifold of dimension 2. In this case, the intrinsic dimension is not constant in the whole space. So we would like a method to retrieve this kind of structure in the actual data. And then I will show you that this kind of situation is not an artificial oddity. So it's clear that it's easy to make an example by just merging data sets with different intrinsic dimensions, you get something with non-uniform intrinsic dimensions. But this kind of situation actually occurs also in natural data, so it's a relevant point. Okay, so the assumptions behind 2NN were that the data points are independent samples from a given distribution and that the density is locally uniform in the region containing the first two neighbors of each point. In order to extend 2NN to the case of a variable d, we make an additional assumptions. So we assume that the distribution rho has support, so is non-zero, only is non-zero on the union of k manifolds with different intrinsic dimensions d1, dk. So there are in the space k manifolds with their own intrinsic dimensions, and the data lie on the union of these manifolds. Under these assumptions, the distribution of the mu, which are the ratios, again, of the distances of the second and first neighbor, follows a mixture of Pareto, is a simple mixture of Pareto distributions. In order to estimate the mixture parameters, among which the most important are the intrinsic dimensions of the surfaces, we use a Bayesian approach. In order to sample the posterior distribution, so we assume a prior on the parameters which are the intrinsic dimensions and the mixture probabilities. If we don't have some prior expectation, you are always free to select a non-informative, a maximally non-informative prior, so it's not a problem. And then we compute the posterior distributions and we estimate the intrinsic dimensions and the mixture probabilities as, for instance, as posterior averages. In order to sample the posterior, we can use a Gibbs sampling scheme. And to do that, we must introduce the so-called latent variables, which represent the manifold membership of each point. So the Z variables are discrete variables that represent to which manifold or to which component of the mixture each point is assigned. And we estimate jointly all these parameters by Gibbs sampling. There is a little problem with this approach, namely it does not work as such. So in the example that I show, for instance, we were trying to apply this in a situation where we had two manifolds, one with fixed dimension d1, and the other we tried to vary. Well, okay, we had several data sets with two manifolds. The dimension of the first manifold was fixed at 4, and the dimension of the second was varying. And we were trying to see whether we were able to find this structure and correctly estimate the dimensions. From the plot, you can see that we could not. So essentially, in this kind of scheme, we were not able to correctly estimate the dimensions. And the problem is actually that we were not able to correctly estimate the z variables. So the assignment of each point to a mixture component was wrong, and this could be seen easily from the mutual information between the true assignment and the estimated assignment, which is in yellow in the plot. I tried to explain you briefly why this happened. The problem is that in mixture problems, it's easy to assign the points if the mixture components are highly non-overlapping. The problem is that Pareto distributions, even with widely different values of d, are highly overlapping. So the assignment of z is not reliable and problematic. Okay, I try to accelerate. So let's say that in order to solve this, okay, this problem shows up in the fact that when you take a small neighborhood around each point, we were finding that all points in a given neighborhood were assigned to different manifolds. I make it very quick. In order to solve the problem, we actually introduce an additional term in the likelihood, which actually, since you're physicists, I finally can say this, it's like a POS term that makes the neighboring, the zeta, that makes the latent variables of neighboring point interact. So we are forcing, essentially we introduce an additional term that privileges configurations where the assignment of neighboring points is the same. And if we do this, we finally are able to correctly assign the points and also correctly estimate the dimensions. We did this in many cases, and what the method does is we are able to find manifolds of different intrinsic dimensions in the data. We did several tests on artificial, which now I skip. The approach also works if you have nonlinear manifolds, if you have topologically complex, like data living on a torus or a sphere or a Swiss roll. In the last 2 slides, I present you an application. We considered a simulation of a villain, which is a very well-studied example in molecular dynamics. This villain is performing folding and unfolding. So we have a long trajectory of the system. We have roughly 30,000 configurations. From each configuration, we extract 32 dihedral angles, and then we apply our dimension variable intrinsic dimension scheme to these 32 dihedral angles. If we do this, we find that the data actually split into 4 manifolds, 3 of which have very low intrinsic dimension and 1 very high intrinsic dimension. What does this mean? In order to interpret the results, we consider the fraction of native contacts, which is a proxy for the degree of folding. So, like configuration with high Q are folded and low Q are not folded. What we found is that the folded configuration essentially all lived in a manifold with high intrinsic dimension, while the unfolded configuration were assigned to the manifolds of low intrinsic dimension. So essentially our scheme is able to find the folded configuration essentially as the points that are living in this high dimensional manifold. Okay, skip this. Let me just recap. So we developed an ID estimator called 2NN, and then we extended it to the case where the ID is variable within a single dataset. The method rests on quite weak assumptions, which are the local uniformity of the density and the dimension. And by applying this method, we can find regions of different local intrinsic dimension in the data. In real data, we actually find large variations of the intrinsic dimension, which highlight relevant structure in the data. I just thank you my collaborators in this project, Alessandro Laio, Antonetta Mira, and Elena Facco. And finally, I thank Aldo Guglielmo for inviting me here today, and also the conference organizers and Aalto University for giving me this opportunity to speak at this prestigious venue. And thank you very much for your attention.
Thank you very much. Questions?
So thank you very much. So my question concerns this assumption that the density is locally constant. So it appears to me that you cannot test this, or can you test it?
Okay, in real data, it's hard because, let's say, in real data, it's hard because I tell you why. The problem is that you can't quite test it. Like you can try to estimate the density and verify if the density is varying very strongly. But most density estimation schemes also rely on the fact that the density is kind of locally constant. So I think it's not super easy to test it. Although I would say that I don't think it's the most critical assumption that we have, because if you have some decent sampling, usually the density is not varying like radically in the space on the scale defined by the first 2 neighbors.
Okay, we have time for while the next speaker prepares. We have another one.
Hello. So I was wondering, actually, why do you think the folded state has a higher intrinsic dimension than the unfolded state? in the case of the protein. One would expect the opposite, right?
Yes. So I think that the problem is what you can effectively, let's say in principle, there might be, so the problem is that the system in principle maybe has lower constraints in the unfolded, or the space of unfolded configuration is larger, but the problem is also if the system is actually able to visit them, because the system, I mean the space of unfolded configurations is much larger in principle, but also the problem is not only whether the space is large, but what the system actually does, and the system actually spends most of its time in the folded configuration, most in terms that compared, like the volume of the folded configuration in phase space is much smaller than the volume of unfolded, but at least half of the time the system is in the folded, and it's exploring many directions in the folded configurations. Yes, at a smaller scale, while in the unfolded it moves along wider, on a wider scale, but it's not actually able to really explore all the possible directions.
Okay, thank you. Yeah.
Thank you.
Thank you.